Welcome to the MIA module titled Targeting Small-Scale Temporal and Spatial Threat Areas. This module is relevant for all convective hazards, but we're going to focus primarily on tornado threats, as there will be other modules that focus on the other storm hazards. This important module in the MIA course aims to help you recognize situations where the near-storm environment can change rapidly in time and space, and how storms can influence that environment. Understand what influences the near-storm environment and how to monitor rapid changes with the tools available. And recognize the ability to target a threat area down to the county or even sub-county level and 1 to 3 hour lead time window, and appropriately message such small-scale threats. Essentially, there are 3 key points that I'd like for you to take away from this module. First, storm environments can change quickly and meaningfully in time and space. Mesogamma, or near-storm scale, may frequently be more important than meso-alpha or meso-beta scales. Secondly, a storm can alter the small-scale environment for other nearby storms. This can lead to small-scale windows of opportunity for tornadoes or other hazards that can rapidly develop within a larger scale, less favorable environment. And third, mesoscale analysis failure is likely to result from the inability to recognize small-scale environment changes. Small-scale focus is where mesoscale environment analysis can succeed or fail for the WFO. Sometimes you'll have clues in radar or satellite that do not appear in the SPC mesoanalysis page or NWP analyses. It can be challenging to accurately incorporate these clues. So why is this topic important? SPC focuses on the larger scale environments and threat patterns. Their focus is on the 3 to 6 hour watches and 12 to 24 hour outlooks. In contrast, the WFO usually focuses on the small scale, generally warning level information. IDSS, however, focuses on communicating more than just warnings. The MIA course focuses on small scale targeted threat messaging from the warning period out to the 2 or 3 hour lead time period, smaller than watch scale. Large-scale environments favorable for severe weather tend to be well forecast because of clear signatures covering large areas, including strong lifting mechanisms, such as a big upper trough, and widespread overlap of instability and shear. This module will focus on the more challenging small-scale hazard threats in time and space, which can be isolated in nature or occur within a larger scale event, with both types illustrated on the lower image to the right. Note the clustering of high-impact events in Texas and Oklahoma within a large-scale severe weather outbreak, as well as clusters of events outside of that area from Iowa down to southern Kentucky. Our focus is on the ability to provide targeted threat messaging on threat potential covering the 1 to 3 hour period ahead of the event, as well as support better warning decisions. The primary difference between hazard environments for large-scale and small-scale events is simply the scale at which favorable conditions for the hazard exists. A tornado outbreak is favorable when we have a large area with a favorable overlap of instability and low-level shear along with lift. A small-scale event tends to occur with very small regions of overlap, or where we have small-scale features such as lifting mechanisms existing within larger-scale fields of instability and shear. The left images show a large area of instability overlap from Kansas southward, while the right images show only a very small area of overlap over southern Georgia where only isolated tornadoes occurred. Let's look at a possible event over the northern plains, and our focus will be on the Dakotas. Based on the images I show you, do you think we're looking at a non-event, a small-scale severe event, or a large-scale event? The 500 millibar pattern shows essentially zonal flow with weak embedded waves. We see an axis, albeit fairly narrow, of sufficient surface space CAPE and minimal SIN across portions of South Dakota into southeastern North Dakota. The same area has decent effective layer shear overlaid, but there's very weak low-level shear and SRH across the Dakotas. At the surface, looking at the wind pattern, we can pick out a weak frontal boundary over eastern South Dakota into western Nebraska. Interestingly, we see moisture pooling on the western side of the boundary with higher mixing ratio values and lower values in the supposed warm sector east of the boundary. And the visible satellite shows the only building cumulus clouds being over the western half of the state of South Dakota. So how would you answer this question? Are we looking likely at a non-event, a small-scale event, or a large-scale event. Hopefully you could assess, based on the features shown, that we're likely appearing to have a small-scale event, mainly across the western part of South Dakota, and indeed we had a very small-scale event just covering that particular area. That was the area where we had a small area of instability and shear overlapping, along with lift from a weak shortwave moving over the area, and potentially some weak surface moisture convergence. The large-scale environment can influence the small-scale. Rapid large-scale environment change relates to rapid small-scale change. Consider a rapidly moving extratropical system, or an inland moving tropical cyclone shown to the right. Local area environment can change quickly. The right animation shows rapid change from an unfavorable to favorable tornado conditions across southern Mississippi during a 3 to 6 hour period, as the SIG tornado parameter, as a reflection of overlapping instability and low-level shear, increases from less than 0.5 to around 2.0. In contrast, a nearly stagnant upper-level pattern away from the tropical cyclone has little influence on the local area environment, thus requiring small-scale features, including convective initiation, to influence the small-scale environment. So what does a tornadic storm respond to for generating the tornado? The large-scale environment or the environment immediately surrounding the storm? The ingredients needed for a tornado to come from the storm are the same regardless of event scale. You need strong low-level vertical shear promoting streamwise vorticity in support of updraft rotation. You need sufficient low-level cape for vortex stretching. And for supercell tornadoes, a downdraft to get the vortex to the surface. The scale by which these ingredients are overlaid dictates the potential scale of the event. And yet the requirements for tornadogenesis are the same regardless of scale. For a given thunderstorm to produce a tornado, the key ingredients above are needed within the environment immediately surrounding the storm. Take a look at this statement. Is it true or false? Given the right setup, a severe thunderstorm or storm cluster can locally modify the storm environment, such as to produce a small tornado threat window in time and space in an otherwise unfavorable large-scale tornado environment. The correct answer is true. This is rather important, as the near-storm environment can be quite dynamic. In fact, storms can influence the environment of other, mostly upstream storms. Storms that otherwise might quickly become severe could end up fairly weak due to environmental stabilization from a prior storm complex that moves across the area, as an example. Likewise, a storm can generate a boundary that brings greater streamwise vorticity to the inflow region of an upstream storm. Let's look at how a storm can locally inhibit or enhance a small-scale window of opportunity for a tornado. Here we see the conceptual structure of a right-moving supercell. This image is from Comet. We not only see a region of enhanced inflow, but also multiple regions of outflow in the forward and rear flanks. Notice the 4 low-level wind profiles for locations A through D. The SPC mesoanalysis page might show a 0 to 3 kilometer SRH value of around 200 meters squared per second squared for the area where the storm is located, but only point B might reflect this, with much higher SRH at point C and much lower values at points A and D. Thus, we have a pattern of SRH resulting from the storm itself that model guidance or the SPC page likely will not show. In this example, which point has a wind profile that appears most favorable for a supercell tornado? In this case, the correct answer would be C, which would support large streamwise vorticity. Point B supports much smaller streamwise vorticity, and point D likely focuses on crosswise vorticity. Think of the profile that causes a football to rapidly spin as it travels in the air, rather than flip end over end. Here's an example of a supercell number 2 that moved through a highly favorable environment for tornadoes and produced a very rare EF3 tornado in far southeast Georgia. However, the storm also produced an outflow boundary that you can see in the reflectivity image, which moves southward. Velocity data showed inbounds on the north side of the boundary, indicating more of a northerly low-level flow rather than easterly or southeasterly in the pre-storm environment. While deep layer shear remained supportive for supercells with decent mesocyclones from the upstream storms, the low-level wind profile became much less favorable for tornadoes, as you can see by the low-level wind profile comparison. Recognition of this prevented far southern Georgia from being under a tornado warning continuously for multiple hours, which likely could have resulted solely from radar-based warning decisions. This illustration shows a boundary along the leading edge of the forward flank downdraft, acting like a frontogenetic warm front with backed and enhanced inflow along it. What other types of boundaries could play a similar role? Consider, of course, an actual east to west oriented warm front with a decent thermal and moisture gradient, along with such oriented pre-existing outflow boundaries or differential heating boundaries that could interact with a storm to produce a small tornado threat window in time and space. Given the supercell image to the right, within a favorable deep shear instability environment for supercell and tornadoes, but also a high LCL environment and weak low-level shear, which would be much less favorable for tornadoes, why might a northeast motion vector shown in black be more favorable for tornadoes? And why might a more eastward motion be more favorable for tornadoes? And finally, in what situation would neither motion vector be favorable for tornadoes? Let's tackle the first one. So in a high LCL environment, a motion vector more east or southeast in this example might keep the updraft in such a less favorable environment, whereas a motion more northeast towards the forward flank downdraft region could support an inflow of more moist air from the forward flank area that could locally lower the LCL, as shown in this model where we see a cloud-based lowering where we have the precipitation. And here's an actual image of a storm with that appearance of a slanted cloud base towards the rain area to the right. The caveat, of course, of this is you can't bring in much cooler, stable area. Of course, you're going to weaken the updraft, and that would not be favorable, of course. What about a more eastward motion? Given a clockwise turning hodograph, a deviate motion more towards the east would support a greater level of streamwise vorticity being ingested into the updraft, a favorable result. Though again, you may be taking the updraft more on a path within a high LCL environment. So neither of these vectors alone necessarily would be suggesting a favorable tornado environment. It may be that a vector in between could capture some decrease in LCL through moistening of the inflow, while also capturing greater streamwise vorticity given a slight deviation more to the right. Given a marginally favorable low-level shear environment for tornadoes, what pre-storm low-level temperature and moisture profile do you think is most supportive of forward flank downdraft and rear flank downdraft boundaries that support tornado genesis? This is a more challenging question. So the left example with dry low levels and a high LCL height would tend to support strong cold outflow. Now there are other vertical patterns of temperature and moisture that also could support cold outflow. Nevertheless, the end result would likely be an outflow boundary that advances away from the storm, cutting off any tornado potential fairly quickly. This could be with any boundary, be it with the forward flank downdraft as well as the rear flank downdraft boundary. In contrast, the middle example suggests potentially minimal outflow. There may not even be a forward flank downdraft boundary with a thermal gradient, and the RFD could be weaker. The right example might be more ideal for producing enough forward flank downdraft cooler outflow to support the scenario shown by the supercell model image, and enough of a rear flank downdraft boundary to wrap around and bring the vortex to the surface. You can probably get a sense here as to why tornadoes are so rare. Everything has to come together just right, especially for getting a stronger, longer-lived tornado. It can be challenging to accurately understand how tornado potential changes with each motion vector without understanding the near-storm pattern of instability, low-level shear, lift, LCL height, and so forth. In a higher LCL environment, for example, a more northeastward motion here could support locally lower LCL, but reduced SRH and possibly colder inflow that weakens the updraft. In a more favorable LCL environment, a more eastward motion along the forward flank downdraft gradient, where surface flow is backed, can maximize SRH, thus greatly enhancing tornado potential. Can you see how mesoanalysis is more than just investigating SPC's mesoanalysis page? These types of storm scale changes may not even appear on that page and require the mesoanalyst to make mental adjustments to the larger scale environment. That's a more advanced skill to have. In addition to supercell tornadoes, occasionally non-supercell tornadoes, some referred to as landspouts, can occur where surface vorticity centers are stretched vertically by new updrafts. Can you see on this image where such vorticity centers could develop? Note northwesterly or westerly flow meeting southwesterly or southerly flow along the rear flank. A new convective tower aligned over such a vorticity center that develops can quickly lead to a short-lived landspout. There are few tools available to forecast this. The SBC mesoanalysis page has a 0 to 3 kilometer cape and surface vorticity display as shown here as an example, but this is designed for larger scale patterns that could support non-supercell tornadoes, not landspouts along the flanking line of a particular storm. A key challenge for the mesoanalyst is keeping up with rapid environment change. Past event failures have resulted from not successfully meeting this challenge. Near-storm environment can change quickly in time and space. For the example below, focus on the western portion of the Oklahoma-North Texas border, which is highlighted by a black oval. Note the rapid increase in the significant tornado parameter in an area where we have favorable overlap of low-level shear and instability that occurs over just a few hours. It also occurs in southeastern Oklahoma. In both areas, we end up with high-end severe weather, including tornadoes. While tornadoes are, in general, a rare phenomena, they are especially rare in areas where CAPE is less than 500 joules per kilogram or 0 to 3 kilometer SRH is less than 150 meters squared per second squared. Getting a surprise tornado in these environments requires storm scale enhancement to support tornadogenesis. How could we get such enhancement to support updraft acceleration? Possibly from enhanced inflow, or even moisture pooling that increases low-level CAPE. How about enhancing SRH to support greater updraft rotation? That could be achieved from back to an enhanced inflow, or deviating storm motion. Let's say pre-storm instability and deep layer shear for the case illustrated below support supercells, but low-level SRH are in the marginal 150 to 200 range. What do the enhanced inflow velocities highlighted below suggest regarding SRH in the storm's inflow region? Likely, a local maximum of SRH is developing. Potentially double or triple the pre-storm environment helicity values. The SBC mesoanalysis page will not show this. Here's a fascinating example. Take a pre-storm environment with a fairly short hodograph, as shown here, thus a marginally favorable environment for tornadoes. How might we locally adjust this environment to be more tornado friendly? Here we see a low top supercell that developed within this environment. Notice how the SRM image on the right illustrates a substantial acceleration of storm relative inflow to over 40 knots. Ground relative, it's likely we're seeing 20 to 25 knots of easterly flow toward the storm. So the inflow region hodograph likely looks more like the bottom example, in which SRH may be double or triple the pre-storm environment value that would normally be shown on SBC's mesoanalysis page. The mesoanalyst needs to mentally adjust pre-storm environment information to account for these storm scale changes. Try answering this question. Why do environments along frontogenetic warm fronts, where we have tightening gradients, tend to be particularly favorable for tornadic storms, and thus an area for targeted threat messaging? Choose all of the correct answers. For this question, all of the choices are correct. Warm fronts or nearly stationary outflow boundaries that act like pseudo-fronts can frequently support small-scale opportunities for tornadic storms, even if the larger-scale pattern of instability, shear, and lift is not ideal. These boundaries can support backed and enhanced low-level inflow that can enhance SRH. Their frontogenetic nature can lead to stronger low-level vertical shear profiles, and they often occur in an area where we can have larger residence times for intense storms to exist. Let's briefly review the tools that we typically use for examining the big picture and how they can be used for smaller scale threat analysis. These tools can include radar, satellite, surface observations, LAPS analyses, the SBC mesoanalysis page, and NWP analyses and short-term forecast output. Of these tools, radar is probably the exception in that it is primarily used for examining the small scale, unless you're viewing a multi-radar mosaic. In addition to looking at storm structure, radar can also show clues to changing storm environment, at least relatively close to the radar site where you can see closer to the surface. The image to the right shows a very slow-moving boundary over southern Kansas, just passing by the Wichita, Kansas radar site. Shortly after this time, a large supercell developed over northern Oklahoma and moved northeast along this boundary, producing a strong tornado over southern Kansas. As for satellite, well, when higher clouds aren't blocking one's view, satellite can be quite helpful in recognizing environmental features, and environment changes in time and space. On the visible image to the right, the arrows show cloud streets oriented differently, more northwest to southeast in southeastern South Dakota, and more north to south in east central Nebraska, suggesting a warm front in between. Also note the cloud streets where the air mass is capped in east central Nebraska and not further west where deep convection is forming. Notice the surface observations overlaid on the satellite image. Over west central Nebraska, the surface observations alone don't show a clear boundary, given a generally southerly surface wind. But by overlaying satellite and also dew point contours, we can see a weak north to south moisture gradient axis along which convection is trying to develop. The surface maps can also be quite useful, but a good surface analysis requires a dense network of observations. Note the difference between surface maps A and B below. You can more precisely locate the boundaries on map B to the right compared to map A. Incorporating other data, such as satellite and radar, can help assess precise boundary locations. Lapse analyses can also be useful for surface analyses. This image is an example of surface divergence, with convergence being negative. It shows the same boundaries as in the prior slide, as represented by the dashed contours of surface convergence. SBC's mesoanalysis page offers a large number of fields for both larger scale and smaller scale environment analysis. An interesting tropical cyclone example is shown for Hurricane Irma in 2017, moving northward up the western side of the Florida Peninsula. Based just on the SPC displays of significant tornado parameter, or STP, and low-level CAPE, can you determine where across northern Florida the late-night tornadoes, including an EF2, will occur? Note that a tornado watch covers most of the northern and central Florida peninsula. However, short-term tornado potential exists where we have an overlap of STP values of 1 or greater, along with a substantial low-level CAPE of at least 50 joules per kilogram, supporting low-level acceleration for vortex stretching. We see these conditions mainly confined to the coastal counties of northeast Florida. Now, the potential for a strong tornado would exist where we have greater values of these fields overlapping. There's only one part of northern Florida where this exists during the night, and that is along the coast in the vicinity of St. Augustine, Florida. The strong tornado occurred just south of St. Augustine. Now, there are other data sets that one could look at to target this threat, but isn't it interesting how well these two fields pinpointed the threat, not further inland where instability was minimal due to widespread rainfall, despite tornado watch coverage. This allowed accurate, targeted threat messaging focused on the coastal counties of northeast Florida. NWP output with regard to small and large-scale environments can be helpful, particularly beyond forecast hour 2 or 3 when observational datasets start to lose value. One of the popular fields to look at from convective allowing models is simulated reflectivity, which can show storm tracks, updraft helicity tracks, hail cores, and so forth. At times, CAM output, including simulated reflectivity, can be quite beneficial, while at other times it can be useless and misleading. Here's an example of the latter, in which the HER, along with others including the high-resolution NAM, indicated no convective initiation in South Dakota during the time that big supercells were actually occurring. Which of the following could be useful clues suggesting enhanced small-scale tornado potential? Choose all that apply. Pause the video if you need to answer this question. For this question, all of the answers, except for H, can be clues to small-scale tornado windows of opportunity. So let's try a case exercise and see if we can accurately target the small-scale threat. Let's apply what's been covered in this module for a case on August 26, 2020 across South Dakota. Our focus will be on targeting threats across that state. It is 20Z, and our task will be to assess threat potential during the 20 to 23Z period, and to communicate our assessment. There's a marginal risk for severe storms during the afternoon and evening across South Dakota. Can we message better during this period than simply communicating a marginal risk of severe storms exists for the rest of the day? Note that no watches have been issued or are planned as of yet for the Dakotas. Aloft, we don't see much to support a significant severe weather threat. Just some weak waves aloft within generally zonal flow. At 850 millibars, we see a front over southeastern or east central South Dakota with an axis of higher moisture west of it. Note that low-level winds are fairly weak over South Dakota, with stronger flow further south and east. At this point, are you able to pinpoint a threat type or area? Likely no, there is not enough information to go on, as you don't know where sufficient instability and deep layer shear overlap, or lifting mechanisms west of the 850 millibar front, which are at the moment uncertain. Let's look at the high-resolution NAM output. Here's the NAM forecast for surface temperatures, dew points, and winds valid at 21Z. You can find a surface front over southeastern South Dakota, closer to what we saw on the 850 millibar analysis. Note the higher dew points that exist west of this boundary, with lower values in the supposed warm sector. You'll also note very warm conditions on both sides of the boundary. Take a look at the surface winds west of the boundary, where dew points are higher, and thus instability should be greater. Do you see any areas of near-surface convergence? The NAM doesn't show much. Here are the NAM 21Z forecasts for Mixed Layer Cape and SIN, showing a weakly unstable but capped warm sector east of the front, and greater instability but some cap further north and west, with the cap becoming minimal in parts of western South Dakota. Here are 21Z NAM soundings for west central and north central South Dakota, showing plenty of instability and deep layer shear, but very little low-level shear. The north central South Dakota sounding still has some mixed layer SIN, which is much less on the west central South Dakota sounding. Both soundings show large downdraft cape as well as large cape in the hail growth zone. Now, despite this favorable overlap of instability and deep layer shear, along with a weakening cap over western and northern South Dakota, high-resolution model guidance doesn't show any initiation of deep convection in these areas during the 20 to 23Z period, perhaps due to the lack of any low-level moisture convergence. Higher level lift might just support mid and high level cloudiness. So now what? Can you pinpoint what will happen and where, if anything at all, during the 20 to 23Z period? Let's see if satellite imagery can help. Afternoon water vapor imagery shows two distinct waves with areas of lift, one that will be moving over and east of the surface front in eastern South Dakota, and another entering western South Dakota. Meanwhile, visible imagery shows something interesting. Other than some weak elevated convection in northeastern South Dakota, there's no convective clouds elsewhere across eastern South Dakota where the surface front is. Just a beautiful sunny day. However, further west, across west central South Dakota, we see a massive building cumulus, suggesting an area of potential moisture convergence that might support deep convection and potentially severe weather. Is this enough to target a threat area, type, and time period in messaging for partners and the public? Well, one could address at least some concern that isolated severe storms could develop in west central South Dakota. Now, could the SPC mesoanalysis page help us target this better and with more confidence? Let's look at some 20Z fields. Surface-based CAPE at 20Z on the right pinpoints a favorable area of strong instability and weak or minimal cap from southeastern North Dakota to west central South Dakota. However, it might be more appropriate to look at mixed layer cape, which narrows this potential to primarily west central South Dakota. This is the area where we saw building cumulus on satellite imagery. What else do you see on these images? Note the surface flow. Unlike the model guidance, which was suggesting fairly uniform northeasterly flow and minimal convergence west of the front, the SPC page suggests an axis of weak convergence near the western gradient of instability, where northeast or east-northeast flow meets up with north-northeast flow. This is where I would be focused, as suggested by visible satellite imagery. The SPC page also shows favorable effective layer shear over this area, but not much in the way of low-level shear, as suggested by fairly low SRH. So unless there is near storm scale enhancement, I would expect very low tornado potential. Recall the fairly weak flow on the 850 millibar analysis. How about wind? We don't have strong low-level flow that could be transported to the surface as strong gusts. However, downdraft cape is very large in the western half of South Dakota, which could support damaging wind potential. How about hail? Here we see cape in the hail growth zone. Values above about 700 or 800 in the presence of shear aloft are quite favorable for very large hail, and this is highlighted across west central South Dakota, along with favorable deep layer shear. Here are some other SPC fields. We have steep mid-level lapse rates, which support the large cape in the hail growth zone, along with large downdraft cape. we see fairly high LCL heights, which would tend to support outflow-dominated storms. The supercell composite and left-moving supercell composite both highlight west central South Dakota. Finally, the significant tornado parameter shows very little, given the lack of low-level shear in SRH. Okay, time to make a final assessment. As the mesoanalyst, what would you want your IDSS person to communicate to partners and the public regarding severe weather potential, if any, during the 21 to 23Z period? Pause this video if you wish to think about it a minute, or go back in the video to review the data. Next, I will show you what I would communicate. There's really only one area I would focus on, and that is along that apparent axis of weak surface convergence within maximum instability overlaid by deep layer shear over west central South Dakota. This was the same area satellite was showing cumulus growing. The green area is where I would scale down the threat message, down to portions of a few counties, and my focus would be on very large hail and damaging winds, with initiation in the next hour or two, given trends again on visible satellite. I have listed the clues that support my focus area. Now, there are other SPC mesoanalysis fields I could have shown, with one being surface moisture convergence. I believed it showed a small area of low values in the vicinity of the green shaded area, which would make sense given the surface wind field and axis of higher dew points in this region. Note that the SPC outlook is likely still valid as a larger scale picture for the region, but I'm focusing on a small scale threat in time and space, one that could yield high-end severe storms. A small-scale, higher-end hail and wind event occurred during the 21Z to 3Z period across west central South Dakota. Several reports of hail up to baseball size and measured winds up to 70 miles per hour occurred. Both left and right movers formed in this area. Here is the MRMS hail swath display for the full event. Our focus was the northern storm cluster that occurred between 21Z and 0Z. You can see both left and right mover hail swaths with hail sizes up to 2 inches or greater. The green area is my approximate outlook area that did fairly well in highlighting the initiation region. Perhaps further observational data could have helped me pinpoint it even better. Here is the SPC reports map showing our event in west central South Dakota, along with other small-scale events across the U.S. that the mesoanalyst could help target. Here's a review of key environmental clues to help target this event. There was moisture pooling, an axis of higher dew points leading to an axis of higher CAPE behind the surface front, rather than in the supposed warm sector. There was lift aloft, as well as through weak moisture convergence to support convective initiation. A combination of large CAPE and deep layer shear supported supercells. Likely a more straight-line photograph supported left and right movers. Large CAPE was seen in the hail growth zone, fueled by steep lapse rates and shear aloft to support very large hail. With high LCL heights and large downdraft CAPE, we also see a favorable environment for severe level winds. The conditions did not favor tornadoes due to high LCL height and weak low-level shear. We had a capped environment that existed prior to 20Z, but eroded over west central South Dakota afterward, as indicated by growing cumulus clouds in that region. SPC issued an MCD at 21Z as the event was ongoing. Prior to convective initiation, could the mesoanalyst have helped the IDSS person craft a targeted threat message that focused on west central South Dakota where cumulus were building, and also the potential that existed for higher end hail and wind? The IDSS person can then generate targeted threat messaging, either a graphic for social media or a message to partners on NDBS chat like the example shown here, an hour or so before warnings are issued. So this is an example of targeted threat messaging ahead of an anticipated small-scale but potentially higher-end event. Here's a summary of the module's key points. Storm environments really can change quite rapidly in time and space, and this can support small windows of opportunity for tornadoes or other hazards within a larger scale area that may be far less favorable. The storms themselves can locally alter the near storm environment for other, particularly upstream storms. The smaller the scale of focus, the greater the potential for failure, and the more critical the mesoanalyst's job becomes to recognize environment change and resulting surprise hazards. Mesoscale analysis failure when it comes to small-scale events typically occurs due to lack of recognition of small-scale environment change. If we can accurately understand thunderstorm environment, and we have accurate conceptual models of what a given environment leads to, then we have a leg up on the radar, and we can anticipate what the radar will show before it shows it, supporting long lead time decisions. Keep in mind that small-scale environment changes may not show up on displays like SBC mesoanalysis or NWP output. It can require the mesoanalyst to have to mentally adjust pre-storm environment conditions to account for these changes, which can be quite challenging at times. You have reached the end of the module, which concludes with a learning assessment provided for your benefit. The assessment's not graded, it simply provides you as a tool to measure your learning. For each question, pause the video as needed to come up with your answer, and write it on a piece of paper. Then continue the video to reveal the answer on the next slide. Do this for each question in the assessment. Good luck.